Alright, so today we're going to talk about Lewis dot structures. So, the first thing we have to talk about are the types of bonds that molecules have. And the three types, okay, they're going to be ionic bonds, covalent bonds, and metallic bonds. Okay. So in ionic bonds, the electrons are transferred They're typically metal with non-metal. Okay, a perfect example would be sodium chloride. Okay, the sodium atom transfers its electron to the chlorine atom. So now I have a cation and an anion, and basically ionic bonds, when I transfer the electrons, they are held together by charge attraction. So remember Coulomb's law. This is what we're talking about. Some space here. Typically metal, non-metal. Okay. Then what do we have next? Next we have, let's see if I can make sure everything's under there. That's a little better. Let's just try that. Okay. Just a little, there we go. Alright. The next one are covalent bonds. And covalent bonds, basically, your electrons are shared. And we typically see them between nonmetals and nonmetals. Okay, and an example of that would be water. We have our hydrogen, and it's sharing its electrons with the oxygen. That's sharing its electrons with the hydrogen. Okay, so we'll talk about what those dots represent. And then last but never least are metallic bonds. And these are metals with metals, right? Just metals. But what happens is that the electrons are pooled. Side. So essentially we have like a sea of electrons that just flow web and go back and forth, kind of like the tides. But the reason that we get a current is that if we put a difference and we do work on it, we're pushing the electrons through, and that allows us to have a current. So an example, of course, would be like sodium metal. Okay, so those are the three types of bonds that we're going to be talking about. The first two are where we're going to spend our time focusing. Okay, so let's talk a little bit about how we're going to denote these, how we draw them. Okay, so when we do this, we're going to talk about Lewis dot structures and valence electrons. Okay, so if we take a look at hydrogen, if we look at the hydrogen atom, it has one proton and one valence electron. And why do we focus on the valence electron? Remember, valence electrons are responsible for our reactions. Okay, so if we take a look at hydrogen, since I have one valence electron, we draw a dot to represent our valence electrons. So this dot is Lewis dot, represents the valence electron. Okay, so helium, the helium atom, has two valence electrons. Remember, it's 1s2. That's my highest principal quantum number. When we draw our helium, we write down the symbol, and we can draw our two dots, just like that. And when you do draw the two dots, whenever you're drawing Lewis dot symbols, make sure you spend some time making these large enough that I know it's not some random mark on your board or on your paper. Okay? Lithium. Okay, when we looked at the electron configuration, it was helium 2s1. Well, helium's the core, so we don't draw these two electrons. We only draw the valence electrons. So you would write lithium and one dot. Okay? What happens if we have more than one valence electron? So let's just do the rest of row 2. So lithium, beryllium has two valence electrons. And notice it's in group 2A. So two valence electrons. Group 2A. And when we do our Lewis dot, notice we're focusing on the main group elements and not the transition elements, because the transition elements, we're filling in the core. We're not filling in our valence electrons. And here in Lewis dot, we're focusing on valence electrons. Beryllium, having two, you could draw it this way, or you could draw it this way. Generally, the way we try to draw it is we imagine a square box. And each side can hold up to two. Electrons. Don't put more than that. Okay? Now, when we do this, some people say, oh, I have two, so I'll just draw a bar. And generally, that's used, but it's much older nomenclature. And personally, I would like you to use the dots. It takes a little longer, but then you can count. This stands for one lone pair, which means it stands for two valence electrons. Okay? So, from beryllium, boron has three valence electrons. So you can draw it like that. Carbon has four. Okay. Nitrogen has 5. Okay. When I draw the lone pair, we'll talk about what that means. When I draw the two electrons on a side up together here, you could have it here, here, here. As long as I see that there are 5 dots around the nitrogen. Oxygen has 6 valence electrons. So I go 1, 2, 3, 4, 5, 6. And again, you'll see us drawing these pairs here and here in different locations, but they need to be on one of those sides around the oxygen atom. Okay? Fluorine has 7, so valence electrons. So 1, 2, 3, 4, 5, 6, 7. Finally, neon has 8 valence electrons. Okay. So I have 1, 2, 3, 4, 5, 6, 7, 8. And so that's how we go about drawing our valence electrons around our atoms. Okay? Notice that when we're talking about this octet rule, what happens is this. Remember, everybody wants to have an electronic configuration, like a noble gas. So the whole goal then for these other atoms is to have what we call an octet. So the octet rule is what drives actually our atoms from either doing ionic bonds or covalent bonds, but it is basically in order to achieve a noble gas configuration. Now, when we talked about hydrogen and helium, remember, hydrogen and helium, okay, are, let me put that in a different color here. So don't forget, for hydrogen and helium, this maxes out at 2 electrons because they only have a 1 s orbital. After that, rows 2 on, you're going to have S and P. You'll include D and F later on, but you have S and P, and those will be your valence orbitals. Okay, and so that's why we have an octet rule. Okay, so let's start with 10.4 and talk a little bit about ionic bonding. So remember, an ionic bond is a transfer of electrons to get cations and anions, right? So we talked about you transfer your valence electrons, your cations and anions. So we know that this is a charge attraction. And what we're going to do is when we talk about ionic compounds, we're first going to look at the Lewis dot and talk about lattice energies, which is quantitative, and then we'll talk about how we can assess the strength of an ionic bond just through qualitative means and the use, not numerically, but a thorough understanding of Coulomb's law. So when we talk about the transfer of electrons, the valence electrons, let's take a look and see how that works. We'll pick our friend sodium chloride. Okay. So if we look at our sodium metal, it has 1 valence electron. Okay. And if we look at chlorine, it has 7 valence electrons. Okay. And I'm going to just move this electron over to this side. Okay. And when we do that, this electron from the sodium ion moves over, gets transferred to the chlorine atom. When that happens, besides me knocking into everything, you're going to get sodium without that electron now, because that electron goes on the chlorine. And I'm going to put that in green, just so you can see where it went. So this electron gets moved over here, it goes right there. So now my chlorine atom becomes a chloride atom, and it has a negative charge. And as we know, opposite charges attract. So now these two are held together by an ionic bond. Okay, we have a charge attraction there. So that's how it works. But then the question is, how much energy does it take to form that bond? what we have is we have what we call a lattice energy. There is some amount of energy that's associated with these two together. So the lattice energy, okay, is the amount of energy, and it could be released or absorbed I'll just say associated with forming, okay, a crystal lattice from 1 mole of cations and cations in the gas state. Okay, and normally we associate anions and cations being aqueous. But here what we're saying is that when I take my sodium ion in the gas state, okay, plus my chloride ion, that too is in the gas state, right? 1 mole of each. When I form my sodium chloride, my crystal lattice, so that's going to be in the solid state, the amount of energy associated with this for 1 mole of my cation and anion is my lattice energy. Okay. Now when we look at a lattice energy, just so you know, it's not something that's easy. I mean, think about ions in the gas state. Okay, so it's not easy to measure. So what we use is we're going to use Hess's law in the form of the Born-Haber cycle. To deduce what, or determine what the lattice energies are. Okay, so let's just go through the steps. Okay, so this is just a diagram for the formation of sodium chloride from basically its elements, which is going to be sodium metal and 1/2 of the chlorine gas. And the heats of formation in this is going to be a negative 411 kilojoules per mole. And if we look at the Born-Haber cycle, so this is my heats of formation. This is what we have here. And we can take the heats of formation and put it into a series of steps. The first is we're going to sublimate sodium, so you're going to go from solid to gas. The second, we're going to break this bond. So 1/2 of CO2, if you break the bond for the bond energy, since there are 2 chlorines, we're going to take 1/2 of that value. So the bond energy, breaking it for chlorine, is right here, to go from chlorine molecule to a chlorine atom. Then if I do my first ionization, I remove my first electron, i.e. 1, ionization energy 1. I get my sodium ion in the gas form. And now if I take my chlorine and I put an electron on it, that's basically an electron affinity. We were talking about that when we were looking at periodic table trends. So finally I have in the gas state my sodium ion and my chloride ion. And when you combine those to form your solid, that is your lattice energy. So even though we can't measure it directly, by using the Born-Haber cycle and being able to measure all these different values, we can derive the lattice energy for essentially any salt that we encounter. Okay, so let's talk about some of the more, let's say, qualitative aspects for it. And what we're going to do is we're just going to talk about the trends that we see in lattice energy, now that we know how it's calculated. So let me remind you about Coulomb's law, which is right here. And you can see two different forms. So basically, Coulomb's law, you can see it in terms of force. So this is the force of attraction. Remember, Q1 and Q2 have to be of opposite charges. So my force of attraction is going to be negative. Okay? If it were the same charge, then my force of attraction would be positive. We know actually it's not attraction, it's repulsion. You could see it as that form, or you could see in the form of energy. Okay, so how much energy is in that bond when we look at the bond for the ionic bond. Now, I put K in here, and you'll obviously it was K. In your textbook, you see it's going to be equal to, it's a constant, it's equal to 1 over 4 pi, and epsilon naught is called the dielectric constant. Okay, so just so you know what everything is. Now the more important part is looking at your trends. So the first one we're going to talk about is ion size. And my chloride ion, since it's all chloride, when we're doing our comparisons, these are all the same size. But as I continue to go down, notice this is n equals 2, n equals 3, n equals 4, n equals 5. In other words, as I go down, we already know this trend, as your principal quantum number increases, as you're going down the column, your shell size increases. So my atoms get larger. Okay? And even though we say, well, wait a second, but I thought the cations are smaller than my neutral atoms. They are, but all of these are cations. We're not comparing to their neutral atom. And you're still increasing in your shell. And because of that, you are increasing, so they're getting larger. So your bond length, which is the center of lithium to the center of your chloride ion, gets longer. Okay? Because it gets longer, since it's on the bottom of your fraction, that means as R increases, F and my energy decrease. Okay? F with respect to 1 over R squared, my energy with respect to 1 over R. So it's inversely proportional to the bond length for energy. Okay? Is this a huge factor? It is a factor. All right? A larger factor, if you had to choose between the two, which you don't, but if you had to, then let's take a look at the charges. Okay? Let's just give you this example. Okay? These values are in your book. The lattice energy is a negative 910 kilojoules per mole for sodium fluoride, and for calcium oxide it's a negative 3,414 kilojoules per mole. Now let's take a look at E. So we're going to assume, if we assume R is the same, then this is a +1, -1. This is a +2, -2. So, neglecting the size differences with R, okay? My calcium oxide is 4 times stronger. The bond is stronger than sodium fluoride. Okay, so, and that's only because of my charge differences there. Okay, now let's take a look at another example then. Okay, and the next example is this. Suppose now you had to compare something like, let's say, magnesium oxide and, let's say, strontium sulfide. Okay? Here, this is a +2, -2, +2, -2, and then let's go ahead and compare it to sodium chloride. +1, -1. So already you know, before you even talk about sizes, since the charges are let's say, emphasized a little more in this, it's more of a contributor to the energetics behind the ionic bond, then you know that of the three, this is the weakest, just by nature of the charge. Okay? Now, if you had to compare these two by nature of the charge, they're the same. So how do you compare the two? So once you know the charge, you can rank it. If the charge differences are the same, so these have the same thing, then let's look at the sizes. This is a smaller, magnesium is smaller than strontium, and oxygen smaller than sulfur. So this has the larger R, distance between the two atoms, which means if it's a larger distance between the two atoms, then between the two, because it's inversely proportional, this is the strongest, because it's small and it has a high charge, and this is in the middle. Okay, so that's how we can start determining. So 1, 2, 3. By understanding the concepts behind Coulomb's law and how the trends and the sizes of our atoms and the charges, we can actually understand the trends in lattice energy, and that will account for probably 90-95% of what we do without having to do any calculations before we even need to move on to the Born-Haber cycle. But it's important to understand how the Born-Haber cycle works and where we get lattice energies from. It's basically derived from Hess's law and from looking at everything else that we can measure.